To our Professor Dr. Callaman and to my classmates, good morning. Today we'll be discussing with you about linear programming in an algebraic approach. I am Mr. Jesse A. Riponte, a teacher of Tugbuk Central Elementary School's PED Center. I am a grade 6 teacher. So this is the topic assigned to me. So our objectives for this morning is to determine slack variables in every constraint. We have solved the optimality of an optimization problem using the simplex method and familiarized the concept of duality in linear programming. Let's start with the slack variables. In an optimization problem, a slack variable is a variable that is added to an inequality constraint to transform it into an equality. Introducing this, the slack variables replaces an inequality constraint with an equality constraint and non-negativity constraint on a slack variable. As with the other variables in the augmented constraints, the slack variable cannot take on negative values, as the simplex algorithm requires them to be positive or 0. If a slack variable associated with a constraint is 0 at a particular candidate solution, the constraint is binding, as the constraint restricts the possible changes from that point. If a slack variable is positive at a particular candidate solution, the constraint is not or is non-binding, as the constraint does not restrict the possible changes from that point. Another is if a slack variable is negative at some point, the point is infeasible or not allowed, as it does not satisfy the constraint. Okay, we'll have an example or examples. Maximize z is equal to 5x plus 6y subject to 2x plus y is less than or equal to 4 and x plus 2y is less than or equal to 4, such that x and y are greater than or less than or equal to 0. With the slack variables, we have 2x plus y plus s sub 1 is equal to 4 and x plus 2y plus s sub 2 is equal to 4. And negative 5x minus 6y plus z is equal to 4. Okay, maximize z is equal to 5x plus 6y subject to 2x. Sorry, same with the other slide. Okay, the simplex method. Most real-world linear programming problems have more than two variables and thus are too complex for graphical solution. So we need to use the simplex method. This method is an algorithm for solving linear programming having more than two variables. Okay, because if we are dealing with two or more variables, it is very difficult to find for the feasible solution using the graphical. The simplex method moves from one better solution to another until the best one is found, and then it stops. Okay, in the simplex method, to solve by using this one, we should follow some steps. We have step number one. The first step of a simplex method requires that we convert each inequality constraint in a linear programming formulation into an equation. Less than or equal to constraints, or the symbol, can be converted to equations by adding slack variables. So these constraints can be converted to equations, provided there are added slack variables, which represent the amount of unused resource. Continuation, we note that slack variables represent an unused quantity of resources. It is added to less than or equal in type constraint in order to get an equality constraint. Artificial variables are added to those constraints with equality and greater than or equal to sign. An artificial variable is added to the constraint to get an initial solution to an LP problem. Artificial variables have no meaning in the physical sense, so they're just artificial variables. Note that also that surplus variables represent the amount by which solution values exceed a resource. These variables are also called negative slack variables. Surplus variables like slack variables carry a zero coefficient in the objective function. It is added to a greater than or equal to type constraints in order to get an equality constraint. Example on the slack variable. Maximize profit z is equal to 7x sub $1 plus 5x sub $1, subject to the LP constraints 2x sub 1 plus x sub 2 is less than or equal to 100, and 4x sub 1 plus 3x sub 2 is less than or equal to 240, such that x sub 2 and x sub 1 are greater than or equal to 0. Solution: to convert this inequality constraint to equalities, we add slack variables s sub 1 and s sub 2 to the left side of an inequality. The first constraint becomes and subject to linear constraints. We have 2x sub 1 plus x sub 2 plus s sub 1 is equal to 100, and 4x plus 3x sub 2, 4x sub 1 plus 3x sub 2 plus s sub 2 is equal to 240. So these are the slack variables so that we can convert into equalities. Okay, the following table represents a comparison between slack, surplus, and artificial variables. We have the meaning, the particulars. We have the slack variable, the surplus variable, and the artificial variable. So the meaning, when you say slack variable, it is unused resources or idle resources. Surplus is the excess amount of resources utilized, from the word itself, surplus. And artificial variable has no physical or economic meaning. It is fictitious. As to when they will be used, the slack variable is used when the constraint is less than or equal to inequality, and for the surplus variable it's greater than or equal to inequality, and for the artificial variable it is for greater than or equal to and equal constraints. For the coefficient in the constraints, for the slack variable it is positive 1. For the surplus it is, as mentioned a while ago, it is the additive inverse, which is negative 1. And for the artificial variable it is positive 1. Coefficient in the objective function z. So for the slack variable it is 0, for the surplus variable it is 0, and for the artificial variable it is positive m for minimization and negative m for maximization problems. As to the use as initial program variable, slack variable is used as starting point or initial table, while surplus variable cannot be used since unit matrix condition is not satisfied, and artificial variable is initially used but later on eliminated. As to the presence on the optimal table, the slack variable helps to interpret idle and key resources. It is surplus variable is not applicable, and artificial variable indicates infeasible solution. Okay, example on problem solving, including or involving Simplex Method. A furniture company produces tables and chairs. Each table takes 4 hours of labor from the carpentry department and 2 hours of labor from the finishing department. Each chair requires 3 hours of carpentry and 1 hour of finishing. During the current week, 240 hours of carpentry time are available and 100 hours of finishing time. Each table produced gives a profit of $7, and each chair produce a profit of $5. How many chairs and tables should be made? Okay, so for the solution for this problem, all information about the example, we have the resource table x sub 1 and the chairs x sub 2 and the constraints. We have the carpentry 4 hours, for the chairs 3 hours, and the constraints is 240. And then for the finishing, we have 2 hours, for x sub 2 is 1 and constraint is 100, and the unit profit is $7 for the tables and $5 for the chairs. Solution. Step number 1. Slack variables are added to objective function with zero profit coefficients. Thus, the objective functions become maximize profit is equal to 7x sub 1 plus 5x sub 2 plus 0s sub 1 plus 0s sub 2. These are the slack variables. To include all variables in each equation, a requirement of the next simplex step, we add slack variables with a coefficient of 1 in each equation. The equations then appear as 2x sub 1 plus x sub 2 plus 1 s sub 1 or plus 0 s sub 2 is equal to 100. And for the other one, 4x sub 2, equation 2, 4x sub 1 plus 3x sub 2 plus 0 s sub 1 and plus 1 s sub 2 is equal to 240. Step 2 is place all the coefficients in a tabular form. So we have this tabular form. So we are going to place all those given coefficients for s sub 1 to 1, 1, 0, 100, and then the right hand side, and 4, 3, 0, 1, 240. Okay. And then the terms and rows that you have not seen before are as follows. We have CJ is profit contribution per unit for each variable. CJ applies to both the top row and the first row. So we have the top row and the first row. While ZJ in the quantity column provides the total contribution or the gross profit in the case of the given solution. So we have the ZJ. Okay. How to find the ZJ? For column x sub 1, it is 0 times 2 plus 0 times 4 is equal to 0. Okay. So 0 times ZJ. Sorry. And then for column x sub 2 is 0 times 1 plus 0 times 3 is equal to 0. For column s sub 1 is 0 times 1 plus 0 times 0 is equal to 0. And for column s sub 2, it is 0 times 0 plus 0 times 1 is equal to 0. For the total profit, it is 0 times 100 plus 0 times 240 is equal to 0. Okay. And step number 3, proceed to the next tableau. Finding the pivot column and the pivot row. How to find? Letter A is, or the first thing is, determine which variable to enter into the solution mix next pivot column. We have the column with the largest positive number in the CJ minus ZJ. And the second one is determine which variable to replace, or the pivot row, to determine the pivot row. To find the pivot row, we divide each amount in the quantity column, the right hand side column, by the corresponding number. The row with the smallest non-negative number is called the pivot row. So we have an example. In our example, we have 100 divided by 2 is equal to 50 for the first row, and 240, so we have 100 divided by 2 is equal to 50, and the 240 divided by 4 is equal to 60. The smaller of these numbers is 50, identifies the pivot row, and the pivot number will equal to 2. Okay, this one. And the step number 4 is variable x sub 1 enters the solution next because it has the highest contribution to profit value, CJ minus ZJ. Its column becomes a pivot column. So this one is the pivot column. To compute new values for the pivot row and to find them, we simply divide numbering we we simply divide the number in the row by the pivot column. 2 divided by 2 is equal to 1. 1 divided by 2 is equal to 1 half. 1 divided by 2 is equal to 1 half, and 0 divided by 2 is 0, and 100 divided by 2 is 50. So everything we just divide by 0. I divide by 2. Okay. Compute new tables for each remaining row. In our sample problems, there have been only two rows in the LP tableau, but most larger problems have many more rows. All remaining rows are calculated as follows. So we have number in new S sub 2 row is equal to number in old S sub 2 row minus the product of number below pivot row in an old row times the corresponding number in the new X sub 1 row. Okay, calculate the new values for the S sub 2. This is then an the example for the rule. Okay, we have 0 is equal to this is 0, and the number in the S sub 2 is 4, and then minus 4 times 1. So 4 times 4 minus 4 times 1 is 4. 4 minus 4 is 0. And then 4 times 1 half is 2, and then 3 minus 2 is 1. And then 4 times 1 half is 2. 0 minus 2 is negative 2. And 4 times 0 is 0. 1 minus 0 is equal to 1. 240 minus this is 200, so this is 40. Okay. Calculate the Zj and the Cj minus Zj rows. Okay, for Zj for X sub 1 column, it is 7. The profit for $7 times 1 plus 0 times 0 is equal to $7. And then for X sub 2, it is 7 times 1 half plus 0 times 1, which is 7 over $2. And 7 times 1 half plus 0 minus 0 times negative 2 is 7 and 1 half dollar. 7 half dollar. And 7 times 0 is 0 plus 0 times 1 is 0. 0 plus 0 is 0. And for the total profit, it is 7 times 50 is 350 times 0 plus 0 times 40 is 0. So 350 plus 0 is equal to $350. Okay, and so on. Okay, for step number 4, because not all numbers in the Cj minus Zj row in the latest tableau are 0 or negative, the solution, that is X sub 1 is equal to 50, S sub 2 is equal to 40, X sub 2 is equal to 0, and S sub 1 is equal to 0, and the profit is equal to $350, is not optimal. We need to proceed to the third tableau and repeat the step number 5. So since it is not optimal, so for the step 1, variable X sub 2 enters the solution next because it is Cj minus Zj is equal to 3 halves is the largest and only positive number in the row. Thus, for every unit of X sub 2 that we start to produce, the objective function will increase by the value of 3 halves or dollars or $1.50. So step number 2, the pivot row becomes S sub 2 row because the ratio 40 over 1 is equal to 40 is smaller than the ratio 50 times 1 half is equal to 100. And step number 3, replace the pivot row by dividing every number in it by the circled pivot number because every number is divided by 1. There is no change. And step number 4 is compute the new values for the X sub 1 row. Okay, we have the explanation. So we have the solution. So 1 minus 0 is equal to 1, and then 1 half times 1 is 1 half. 1 half minus 1 half is 0. 1 half times negative 2 is negative 1, and 1 minus negative 1. 1 half minus negative 1 is minus negative 1 is just 1 half plus 1 is 3 halves. And then 1 half times 1 is 1 half. 0 minus 1 half is negative 1 half. And 1 half times 40 is 20. 50 minus 40 is 30. And step number 5, calculate the same process, repetition of the steps. and this time the profit is $410. Okay, next, because every number in the third tableau CJ row is 0 or negative, we have reached the optimal solution because this is our target in the CJ minus ZJ row should be 0 or negative. And we have reached the optimal solution. The solution is x sub 1 is equal to 30, x sub 2 is equal to 40, and s sub 1 is equal to 0 slack in the first resource, and s sub 2 as well as 0. And the profit is $410. So, going back to the problem, at least 30 tables and 40 chairs will be produced to get a maximum profit of $410. Okay, that's all for my report. Thank you very much for watching and listening.